Hello and welcome. Before we begin our journey to the stars, make sure to subscribe so you never miss a chance to explore the universe in calm, slow detail. Tonight, we'll drift toward Alpha Centauri, a nearby star system, and discover the quiet science behind its stars, planets, and the forces that shape them. Relax, breathe slowly, and let curiosity guide you as we watch how the universe unfolds in real, observable ways. Let's begin by observing our closest stellar neighbor and the delicate balance that makes its worlds what they are. You turn your attention outward, beyond the quiet glow of your familiar night sky, toward the constellation of Centaurus. There, just over 4 light-years away, lies Alpha Centauri, the closest star system to our own Sunday. This proximity does not make it simple, but it does make it tangible. Every photon arriving from this system carries information about mass, composition, and motion. You follow these signals carefully, letting them guide your understanding of stars beyond your solar neighborhood. Alpha Centauri is not a single star, but 3 distinct ones, arranged in a delicate gravitational balance. Alpha Centauri A is the largest, a G-type star very similar to your Sun in temperature and brightness. It radiates steadily, providing a familiar reference for your measurements. Its companion, Alpha Centauri B, is slightly smaller and cooler, classified as a K-type star. The interplay of these 2 primary stars forms a binary orbit, completing one cycle approximately every 80 years. You can imagine the slow, predictable paths they trace, a slow cosmic dance governed by gravity and nothing more. Then there is Proxima Centauri, a faint red dwarf orbiting the binary at a far greater distance. Its luminosity is lower, its mass only a fraction of the Sun's, yet it holds its own significance for observation. You notice that its light reaches you at a different wavelength than the brighter stars, and this difference allows instruments like the James Webb Space Telescope to separate its signal from the others. Its presence demonstrates that even small stars can exert long-term gravitational influence, subtly shaping the motions of any potential planets around them. As you trace the geometry of this system, you become aware of the distances involved. Alpha Centauri A and B are roughly 23 astronomical units apart at their closest approach, comparable to the distance between the Sun and Uranus. Proxima orbits the pair at about 13,000 astronomical units, a vast separation, yet still gravitationally bound. These numbers are not abstract. They anchor your perception of scale. Light, traveling at 299,792 kilometers per second, takes just over 4 years to bridge the gap from these stars to your eyes. You feel the vastness of space not as a concept, but as a measurable, observable reality. You watch how astronomers use this proximity to their advantage. Nearby stars provide opportunities for detailed study that distant stars cannot.
Spectroscopie révèle chemical composition.
Variations in brightness indicate surface phenomena, rotation, or orbiting companions. Careful measurement of proper motion, how stars appear to move across the sky, allows for precise mapping of their positions and trajectories. The motions of Alpha Centauri A and B, observed over decades, yield reliable estimates of mass and gravitational influence. These observations provide a foundation for testing your models of stellar evolution. You notice that Alpha Centauri's motion is not random. It shares a general path with your Sun through the galaxy, moving in the Milky Way's local arm at a velocity of roughly 20 kilometers per second relative to nearby stars. This common motion helps establish a frame of reference for measuring other stellar systems. You can predict where Alpha Centauri will appear in the sky decades from now, and compare those predictions with actual measurements. The agreement reassures you that your understanding of gravitational dynamics is solid, grounded in repeated observation. The brightness of Alpha Centauri A and B provides further clarity. You consider the way sunlight illuminates your own surroundings. A-type stars are brighter, but these stars' relative dimness allows you to study subtle features without the blinding glare of more luminous objects. Photometric data, collected over time, shows tiny fluctuations in brightness caused by rotation, star spots, and magnetic activity. These variations are not random. They reveal internal processes within the stars, the movement of plasma, and the cyclical patterns of energy release. Red dwarfs like Proxima Centauri behave differently. Their smaller mass leads to longer lifespans and more frequent magnetic activity. You follow the patterns of flares, noting how they increase temporarily the brightness at specific wavelengths. Infrared observations detect heat from these events, which, though small in energy relative to the larger stars, have an outsized influence on potential planets nearby. Understanding these flares allows you to calibrate expectations for habitability and atmospheric stability. As you consider the possibility of planets, you notice how Alpha Centauri provides a laboratory for studying exoplanetary systems. The binary stars' orbits affect the stability of planetary paths. Planets must occupy zones where gravitational forces from both stars are not destructive over long timescales. You observe that even small perturbations can shift orbits gradually, a process measurable across decades. These effects reinforce your understanding that celestial mechanics is predictable, yet delicate, and that observation remains the most reliable guide. You absorb the rhythm of the stars' cycles, their light arriving steadily, carrying evidence of nuclear fusion deep within their cores. In Alpha Centauri A, hydrogen fuses into helium at a rate almost identical to the Sun, generating energy over billions of years. B, cooler and slightly smaller, has a slower fusion rate, radiating less energy but following the same physical laws. Proxima Centauri burns dimly, its energy output modest but continuous. You recognize that all stars, regardless of size, are governed by identical principles of physics, and that careful measurement can reveal these principles in action. Through careful timing of their brightness and precise tracking of position, you witness how these stars interact gravitationally. The binary stars create a slow oscillation in their motion, predictable and measurable. Proxima's distant orbit introduces long-period variations. You understand that the system is stable, yet dynamic, providing an ideal natural laboratory for testing theories of star formation and orbital mechanics. You reflect on the fact that Alpha Centauri is not exotic, but exemplary. Its closeness allows detailed study, yet it behaves according to the same laws that govern more distant stars. This proximity enables direct comparison with your own sun, helping you refine models of stellar structure, energy output, and long-term evolution. Observing Alpha Centauri reassures you that the universe, though vast, is comprehensible through patient measurement. In the quiet of the night, as you absorb light that has traveled years across empty space, you feel the order and scale of the cosmos. Each observation strengthens your sense of spatial awareness, the relation of distance, mass, and motion. The measurements, though collected by instruments and analyzed with equations, translate into an intuitive understanding of where you sit in the galaxy. The regularity of stellar behavior, the stability of orbits, and the predictability of light crossing interstellar space leave a sense of calm certainty. You let your mind linger on this system, noting that even the smallest star, Proxima Centauri, plays a role in shaping potential planetary environments. The alignment of gravity, distance, and energy output provides a pattern that is measurable and testable. You feel a quiet satisfaction in knowing that the universe offers these observable truths, accessible to those who watch patiently. The light from Alpha Centauri carries more than position or brightness. It carries the history of nuclear processes, magnetic activity, and orbital interactions. You realize that even nearby stars, familiar in terms of distance, hold complexities that take decades of observation to fully quantify. These observations deepen your understanding not only of the stars themselves but also of the delicate balance that allows planets to exist in stable orbits. As you trace the trajectories and examine the stellar characteristics, you begin to notice subtle variations in light that suggest the presence of circumstellar material or faint planetary companions. The evidence is careful, measured, and precise. You absorb the understanding that astronomy is less about sudden revelations and more about the patient accumulation of data over time. Each photon from these stars has a story encoded in its wavelength, arrival time, and intensity, and each contributes to your growing knowledge of the system. The night grows quieter, and your mind rests with the observation that Alpha Centauri, though close, is a microcosm of the broader galaxy. The study provides both reassurance and curiosity. Reassurance that stars follow the rules you can measure and predict, and curiosity because even the closest stars continue to reveal subtle, measurable phenomena. Light years away, yet intimately connected to your measurements, Alpha Centauri invites you to consider not only the stars themselves but also how every orbiting object, every flare, every subtle wobble tells the ongoing story of cosmic motion. You allow yourself to pause with this understanding, feeling the gentle, predictable rhythm of three stars moving through space. Their interactions, light and energy form a pattern you can trace, and in tracing it, you are already beginning to consider how planets might respond to such a complex stellar environment, and what signatures those planets might imprint upon the light that eventually reaches your instruments. You shift your focus from the stars themselves to the tools that allow you to study them in detail. The James Webb Space Telescope orbits far from Earth, positioned at the second Lagrange point, L2, a stable location where gravitational forces and orbital motion balance. From this vantage point, Webb experiences a steady environment, free from the thermal fluctuations and atmospheric interference that limit ground-based observations. Every instrument is designed to detect light in the infrared spectrum, wavelengths longer than those visible to the human eye. You follow the science carefully, understanding that this choice is deliberate, not arbitrary. Infrared light carries information about temperature, composition, and movement. Warm dust, gas clouds, and faint stars emit strongly in these wavelengths, allowing Webb to detect objects that are otherwise invisible. You note that Alpha Centauri, although bright invisible light, reveals additional details in infrared, such as subtle thermal variations across its surfaces and the presence of circumstellar material. The telescope does not roam randomly. It observes specific targets, chosen based on scientific value, proximity, and feasibility. Each observation requires careful calculation to ensure that the detectors remain stable and accurate. Webb's instruments must operate at temperatures close to absolute zero. You imagine the heat shield, a 5-layer structure larger than a tennis court, reflecting sunlight and radiated heat away from the telescope's sensitive components. Even the smallest thermal fluctuation could blur images or mask faint signals. By maintaining this extreme cold, Webb allows its sensors to detect the faint infrared light from distant stars and potential planets. You appreciate that the telescope's positioning, orientation, and thermal control all work together to create an environment conducive to precise measurement. You consider the importance of diffraction and angular resolution. Every telescope, regardless of size, is limited by how finely it can separate light from closely spaced sources. Alpha Centauri's binary stars are separated by only a fraction of an arcsecond as seen from Earth. The infrared light from both stars reaches Webb nearly simultaneously, but the telescope's mirrors and detectors are designed to distinguish between them. You notice that the combination of mirror size, optical design, and instrument sensitivity enables the separation of signals that would otherwise merge. This is essential for studying each star individually and any planets that may orbit them. Observations are not instantaneous. Webb collects data over hours or even days, integrating light to detect faint features. You imagine each photon as a small messenger, carrying information across 4 light-years, arriving one by one and gradually building a coherent picture. The telescope records this light, measuring intensity at different wavelengths. By comparing these measurements across time and wavelength, astronomers identify patterns that reveal surface temperature variations, stellar flares, and potential planetary transits. You recognize that each observation is a careful accumulation of evidence, requiring patience and precision rather than dramatic discovery. You also note the influence of the telescope's field of view. Webb cannot observe large areas of sky at once. Each pointing is deliberate, targeting regions where high-priority science can be conducted. Nearby stars, like those in Alpha Centauri, are ideal because small changes in brightness or spectral signature are measurable with high confidence. For distant galaxies, Webb must collect light for longer durations, often stacking images to detect faint structures. You understand that proximity provides clarity, allowing direct study of individual stars and their immediate surroundings. The design of Webb's instruments further refines observations. The near-infrared camera captures light in the range from 0.6 to 5 microns, revealing stellar surfaces, dust disks, and potential planetary shadows. The mid-infrared instrument extends coverage to longer wavelengths, up to 28 microns, where cooler objects and thermal emissions appear. Each instrument has filters and dispersive elements that separate light into detailed spectra, showing absorption lines caused by specific molecules. You follow this process gently, noting that every spectral feature has a precise physical meaning, representing the interaction of photons with matter. Webb's observing strategy also accounts for motion and stability. Stars move slightly relative to background objects due to proper motion. Earth's orbit around the Sun introduces apparent shifts in position. The telescope compensates for these movements using fine guidance sensors that track reference stars, maintaining pointing accuracy within milliarcseconds. You perceive the care taken to ensure that measurements are not contaminated by motion blur, that each photon is accurately attributed to its source. The telescope is a delicate instrument in a precise environment, capable of turning faint signals into reliable data. You notice how data is transmitted back to Earth. High-gain antennas relay gigabytes of information, which are then processed to remove cosmic rays, instrumental noise, and thermal fluctuations. Scientists reconstruct images, spectra, and light curves from this raw data, interpreting every variation with attention to error and uncertainty. You feel the slow, deliberate process of observation and analysis as a rhythm, where patience and precision are essential. Science unfolds quietly, without urgency, but with enduring reliability. Even the schedule of observations is a form of careful planning. Webb's time is allocated months in advance, ensuring that high-priority targets receive sufficient exposure. Observing windows for Alpha Centauri consider its position relative to the Sun, Earth, and Moon, as well as the orientation required for the heat shield to remain effective. You understand that these constraints do not limit discovery. They structure it, allowing optimal conditions for gathering meaningful information. Through all of this, you recognize that James Webb does not look in the human sense. It measures, it collects, and it translates photons into interpretable signals. Its observations are deliberate, guided by physics and engineering, and informed by prior knowledge. Alpha Centauri benefits from this approach because its stars are bright, close, and well-characterized, allowing repeated, precise measurements that refine your understanding of stellar behavior. You appreciate the clarity that proximity provides, revealing details that would be imperceptible in more distant systems. You reflect on the telescope's role in confirming existing knowledge. Every observation of Alpha Centauri serves to strengthen models of stellar mass, temperature, and luminosity. By measuring light at multiple wavelengths, astronomers test predictions about nuclear fusion rates, surface activity, and orbital dynamics. Even the absence of expected features is informative, reinforcing confidence in the models. You feel the reassurance of verification, a quiet certainty that comes from observing nature with well-calibrated instruments. As you follow the science, you notice the subtle patterns in the collected data. Variations in brightness suggest rotation and surface phenomena. Infrared excess hints at circumstellar dust, potential remnants of planet formation. Slight shifts in spectral lines reveal gravitational interactions and radial velocity changes. Each signal is small, precise, and measurable. You sense that the universe is comprehensible when approached with careful observation and patient measurement, and that the telescope is your instrument for translating faint light into knowledge. You let yourself rest with the understanding that James Webb's gaze is both focused and deliberate. Its infrared vision, thermal stability, angular resolution, and precise timing combine to provide a detailed, measurable view of nearby stars. Observations of Alpha Centauri are not instantaneous revelations, but carefully built mosaics of light, recorded over hours and days, interpreted through well-understood physics. The telescope reveals subtle phenomena that improve models, refine predictions, and guide expectations for potential planets. Every photon collected reinforces the patterns you already understand and hints at the complexity of what remains unseen. You feel the measured rhythm of observation, the slow accumulation of knowledge, and the certainty that arises from repeated, precise measurements. In this quiet space, you understand that deliberate observation is the foundation of understanding the cosmos. The stability of Webb, its carefully planned infrared observations, and the clarity it provides allow you to perceive the subtle signatures of planetary environments and stellar behavior. You begin to consider how these observations can inform the search for planets, their atmospheres, and the influence of stellar activity on habitability, creating a continuous thread of scientific inquiry that stretches from photon to planet. You turn your attention to the intricate task of distinguishing multiple stars within the same system. Alpha Centauri presents a particular challenge because its two primary stars, A and B, orbit each other closely while Proxima Centauri drifts at a much greater distance. From Earth, they appear nearly aligned, and without careful instrumentation, their light would blur together. You notice that separating the light from each star requires not just powerful optics, but a deep understanding of physics, measurement, and observational geometry. Angular resolution becomes your first point of focus. This concept describes the smallest angle over which a telescope can distinguish two distinct sources of light. For Webb, the large 6.5-meter primary mirror provides an exceptional ability to resolve fine details. You think of the mirror as a precise collector, capturing incoming photons and focusing them sharply onto detectors. The larger the mirror, the smaller the angular separation it can resolve. Alpha Centauri A and B, while close in physical distance, are separated by enough angle from Webb's perspective that careful observation allows them to be studied individually. You observe that diffraction, a natural consequence of light passing through an aperture, sets a theoretical limit to resolution. Every telescope must contend with this effect. Webb's design minimizes diffraction through its segmented mirrors, which are carefully shaped and aligned to produce a coherent wavefront. Tiny gaps and edges are accounted for in optical modeling, ensuring that each photon maintains its correct path to the detectors. You recognize that this technical precision allows astronomers to distinguish the two brighter stars despite their apparent proximity in the sky. Proxima Centauri adds an additional layer of complexity. Its faint infrared light is dwarfed by the brightness of A and B, yet its physical separation in space, though large, still places it near enough that scattered light could interfere with detection. Webb's infrared instruments handle this challenge with careful calibration. You follow the strategy. Exposure times are adjusted, filters are selected to emphasize specific wavelengths, and data processing algorithms subtract background contamination. The goal is to isolate each star's unique light signature without artificially altering its properties. Spectroscopy provides another essential tool. Light from a star contains a spectrum, a series of absorption and emission lines that reflect the elements present in the star's atmosphere. Each star has subtle differences in its spectrum due to temperature, composition, and magnetic activity. By analyzing these lines, astronomers can distinguish photons from Alpha Centauri A versus B. Even if their apparent positions overlap slightly, spectral separation allows you to identify which star contributes each fraction of light. You notice that spectroscopy is a form of measurement that complements spatial resolution, enabling a dual approach to clarity. You consider the role of point spread functions, the pattern produced by a telescope when imaging a point source. Every star, even if perfectly distant, produces a small, measurable blur. By modeling this pattern for each star, Webb's data processing can deconvolve overlapping signals. Subtraction of one star's contribution from the combined image allows the other star to emerge clearly. You understand that this method requires patience and precision, not speed, and that the resulting images are the product of careful calculation as much as direct observation. Infrared wavelengths assist further in distinguishing these stars. While visible light from A and B is bright, their infrared emissions differ slightly due to temperature and surface characteristics. Proxima's cooler, redder infrared signature stands out when viewed with appropriately tuned filters. You imagine the detectors recording photons in multiple channels simultaneously, each capturing a different portion of the infrared spectrum. By combining these channels, astronomers can build a composite picture that separates the contributions of each star. The process is methodical and precise, producing clarity without exaggeration. You note that orbital motion also aids separation. Over time, Alpha Centauri A and B move relative to each other, slightly altering their angular positions. By observing the system across months or years, astronomers can track these shifts, refining models of orbit, mass, and light contribution. This dynamic perspective allows incremental improvements in resolving individual stars. Even small changes in relative position are measurable, emphasizing the importance of temporal observation. Calibration is another essential aspect. Webb's detectors are sensitive to tiny variations in temperature, cosmic rays, and electronic noise. Each exposure must account for these factors to ensure that observed differences in brightness or spectral features are intrinsic to the stars themselves. Flat fielding, dark current subtraction, and careful detector characterization remove systematic errors. You feel the deliberate, patient rhythm of these procedures, a steady, unhurried method of ensuring that every photon contributes to reliable knowledge. Background stars and interstellar matter must also be considered. Even in a nearby system like Alpha Centauri, light from distant sources can overlap faintly with the stars of interest. Webb's field of view is chosen to minimize such interference, and background measurements are incorporated into data reduction. You recognize that clarity does not come from removing complexity, but from accounting for it carefully and methodically. Every subtle source of light is quantified, leaving only the signal that belongs to the target stars. You notice that high dynamic range imaging plays a role. Alpha Centauri A is brighter than B, and both outshine Proxima Centauri. Webb's instruments can adjust exposure times and detector settings to capture both bright and faint objects simultaneously. Multiple exposures with varying sensitivity are combined to produce a single image where details of all three stars are preserved. This technique ensures that the faintest signals are not overwhelmed by the brightest, allowing a complete picture to emerge. You understand that separating light is not an act of discovery in itself, but a prerequisite for deeper understanding. Only once each star's light is isolated can you study surface activity, stellar composition, or signs of orbiting bodies. Alpha Centauri becomes a controlled experiment in observational technique. The stars do not change for your benefit. You simply adjust your instruments, methods, and measurements until the signals can be interpreted reliably. This patient process is as much a part of astronomy as recording a new flare or detecting a planet. You reflect on the importance of patience in observation. Each photon recorded over hours, days, or months contributes to a gradually clarified image. Small errors, unaccounted effects, or scattered light could obscure understanding. By methodically separating signals, calibrating instruments, and analyzing spectra, astronomers transform overlapping light into precise information. You recognize that this careful approach is the foundation of accurate knowledge and that clarity emerges not from luck, but from sustained measurement and analysis. Even the faintest variations in light are informative. Rotation-induced brightness changes, magnetic flares, and subtle thermal fluctuations are all detectable once the star's contributions are distinguished. Proxima Centauri's sporadic flares, which might otherwise be hidden in the glare of A and B, reveal themselves clearly. You appreciate that every detail, no matter how small, can be extracted through deliberate, evidence-based observation. The stars become not a blur, but a set of measurable, separable entities. You allow your mind to linger on the precision required to achieve this clarity. Light from 3 distinct stars, traveling over 4 light-years, arrives at your instruments simultaneously, carrying a combination of brightness, spectrum, and timing. By understanding optics, spectroscopy, motion, and calibration, you can disentangle these signals and assign them to their sources accurately. The process is a testament to the power of patient observation and methodical analysis. In this environment of careful measurement, you see that astronomical clarity is rarely instantaneous. It emerges gradually, photon by photon, spectrum by spectrum, guided by the physical principles of light, optics, and motion. Separating the light from 3 suns does not require dramatics. It requires steady observation, meticulous methodology, and the careful application of established physics. Each resolved photon contributes to your knowledge, allowing you to understand individual stars, their behavior, and the environments they create around them. The patterns in the light, once separated, offer insight into surface activity, orbital mechanics, and potential circumstellar material. You notice that the interplay of resolution, spectroscopy, and calibration provides a view that is both precise and quiet. Each piece of information is measurable, reproducible, and interpretable, revealing a universe that is orderly, structured, and accessible to careful study. The separation of light allows you to perceive each star as distinct, yet connected by gravity and shared history. You sense the subtle influence each exerts on its companions and the faint traces of matter that may orbit around them. Through careful observation, light that traveled years across space becomes an instrument of understanding, revealing structure, dynamics, and composition in ways that feel gentle, patient, and deeply satisfying. Your attention rests on Proxima Centauri, the smallest of the 3 stars in the Alpha Centauri system. Its diminutive size does not diminish its importance. Despite its faintness in visible light, it is the closest red dwarf to your Sun and offers a unique opportunity to understand this abundant class of stars. Red dwarfs, classified as M-type, have masses ranging from roughly 10 to 60% of the Sun's. Proxima Centauri sits near the lower end of this range, emitting far less energy than either Alpha Centauri A or B. You notice that its light is mostly infrared, invisible to human eyes but detectable by instruments like the James Webb Space Telescope. You consider the longevity of red dwarfs. Their smaller mass means that nuclear fusion proceeds at a slower rate. While your Sun has a total lifespan of roughly 10 billion years, Proxima Centauri could remain on the main sequence for trillions of years. Its fuel, primarily hydrogen, is consumed gradually, giving it an incredibly long, stable period of activity. You understand that the slow pace of fusion allows the star to maintain a relatively steady output over durations far exceeding the current age of the universe. Despite this stability in energy production, red dwarfs display a high degree of magnetic activity. You note that the star's small size and rapid rotation contribute to strong magnetic fields. These fields emerge from the motion of conductive plasma within the star's interior, generating frequent flares and stellar storms. Observations show that Proxima Centauri produces flares capable of temporarily increasing its brightness across ultraviolet and X-ray wavelengths. You perceive that this activity is not occasional, but a regular feature of the star's behavior, creating an environment markedly different from the relatively calm Sun. Flares are a key factor when considering the star's surrounding space. Proxima Centauri's magnetic eruptions release bursts of energy, sending charged particles streaming outward at high velocities. These stellar winds interact with any planetary atmospheres, stripping away lighter elements over time. You realize that the potential for habitability is constrained not only by distance from the star, but also by the intensity and frequency of these flares. Even planets located within a nominal habitable zone may experience extreme radiation exposure, influencing surface conditions and atmospheric retention. You observe that flare frequency varies with the star's age and rotation rate. Younger red dwarfs rotate rapidly and produce more frequent and powerful flares. Over billions of years, rotation slows and activity decreases, yet even older red dwarfs maintain flaring behavior at a lower level. Proxima Centauri, with an estimated age of 4.85 billion years, exhibits moderate flare activity, sufficient to affect any closely orbiting planets. You appreciate that the physical mechanisms behind these flares are well understood, grounded in the behavior of plasma, convection, and magnetohydrodynamics. Rotation plays a central role in magnetic activity. You notice that the star's convective interior allows energy and charged particles to move efficiently, generating a magnetic dynamo. This mechanism strengthens the star's magnetic field and produces localized regions of intense activity on the surface. Star spots, analogous to sunspots but often larger relative to stellar size, appear where magnetic flux inhibits convection. As the star rotates, these spots alter the light received at precise intervals, measurable as small fluctuations in brightness. You follow the logic of how these variations provide insight into the star's rotation and magnetic cycles. You reflect on how these properties influence the potential for planetary habitability. Any planet orbiting Proxima Centauri would likely be close to the star, because the low energy output necessitates a short orbital distance to maintain liquid water. This proximity amplifies the effects of magnetic activity and flares. Tidal forces could cause the planet to become tidally locked, presenting the same face to the star at all times. The combination of intense radiation, close proximity, and slow rotation creates a dynamic environment for atmosphere retention and climate patterns. You notice that the rules of physics predict these outcomes, offering precise, evidence-based constraints on what planets might experience. Infrared observations help detect such effects indirectly. By measuring the star's flux in different wavelengths, you can infer surface temperature variations and flare events. James Webb's instruments capture these subtle fluctuations, revealing patterns of energy emission that would otherwise remain hidden. You recognize that observational astronomy does not rely on dramatic visual impressions, but on carefully quantified measurements that convey real physical properties. Each observation reinforces the understanding that Proxima Centauri is active, but predictable within the framework of stellar physics. Stellar activity also affects planetary atmospheres through ionization and chemical changes. High-energy radiation can break molecular bonds, alter atmospheric composition, and influence potential biosignatures. You see that models of atmospheric retention must consider the frequency and intensity of flares, the planet's magnetic field strength, and the rate of atmospheric replenishment. Proxima Centauri becomes a natural laboratory for testing these principles, a nearby example of how stars shape the environments of orbiting bodies. The combination of measurement, physics, and modeling provides a detailed understanding without speculation. You contemplate the role of Proxima Centauri as a representative red dwarf. Approximately 70% of stars in the Milky Way are red dwarfs, making them the most common stellar type. Observing this star gives insight into the majority of planetary systems in the galaxy. You notice that while many red dwarfs are smaller and dimmer than your Sun, their magnetic activity introduces constraints that are important when evaluating habitability on a galactic scale. Understanding one red dwarf in detail allows you to generalize cautiously to others, with attention to mass, age, and rotation rate. You consider Proxima Centauri's orbit relative to Alpha Centauri A and B. Its vast separation means that it is gravitationally bound but exerts minimal influence on the primary binary pair. The light from Proxima reaches you slightly delayed compared to A and B, but its signals remain distinct. By isolating this light, you can study flares, spectral lines, and surface characteristics individually. The star's faintness requires careful integration over time, yet the data that arrives is precise, revealing both constant and variable features. The star's behavior becomes comprehensible through consistent observation and careful analysis. Magnetic flares also produce observable effects in the surrounding space. Charged particles interact with interstellar material, sometimes producing detectable radio emissions. These emissions, when measured, provide an additional layer of information about the star's environment and activity cycles. You notice that these signatures are subtle, requiring sensitive instruments, but they offer a comprehensive picture of stellar dynamics. The quiet accumulation of this data reinforces the understanding that even a small, faint star has measurable influence on its surroundings. Through all of this, you perceive that proximity does not guarantee stability. While Alpha Centauri A and B may provide a relatively calm environment, Proxima Centauri's activity demonstrates that nearby stars can create extreme conditions for orbiting planets. Understanding the star's behavior, its magnetic cycles, and its flare activity allows you to assess environmental limits with precision. You notice that the tools, observations, and models work together to form a coherent picture, each element reinforcing the other. You allow yourself to consider the implications gently. Planets around Proxima Centauri, while potentially located in a habitable zone, experience conditions that differ significantly from Earth's. Radiation exposure, tidal locking, and atmospheric erosion are measurable constraints, derived from well-established stellar physics. This understanding does not diminish the star's importance. It highlights how physical properties dictate outcomes for nearby bodies. Observation provides clarity, allowing you to assess reality without uncertainty or speculation. The slow, steady accumulation of measurements conveys a quiet certainty. Each flare recorded, each spectral line analyzed, and each variation in brightness contributes to a detailed understanding of this small but active star. You recognize that Proxima Centauri, like all stars, follows the rules of physics, and that careful study allows even faint, distant signals to inform you about stellar behavior, planetary potential, and magnetic dynamics. Your focus shifts from stars to the planets that may orbit them. James Webb provides a unique opportunity to study exoplanet atmospheres, but the process is subtle and precise. You consider how the telescope observes a planet not by imaging it directly, but by measuring the light from its host star as the planet passes in front or behind it. Each transit produces a tiny change in brightness, just a fraction of a percent. Yet this variation carries information about the planet's size, orbit, and atmospheric composition. Infrared light plays a central role. As a planet moves across the face of its star, molecules in its atmosphere absorb specific wavelengths of light. These absorptions appear as dark lines or features in the spectrum of the star's light. Each molecule, whether water vapor, carbon dioxide, or methane, leaves a distinct signature. You follow the logic. By analyzing these patterns, astronomers can infer the presence and abundance of atmospheric constituents. Even faint signals become meaningful when combined across multiple transits, building a precise picture over time. The clarity of these measurements depends on several factors. The brightness of the star, the size of the planet, and the planet's orbital inclination all influence the detectability of atmospheric features. Close, bright stars like Alpha Centauri provide strong signals, yet even in these favorable cases, the variations are extremely small. Webb's instruments must remain stable, and data must be collected over many hours or repeated transits to reduce noise. You notice that patience is essential. Meaningful results arise not from a single observation, but from careful accumulation and analysis. You consider the limitations imposed by distance and planet size. Smaller planets produce smaller dips in stellar brightness, and their atmospheres absorb less light, making detection more challenging. A planet with a thin or cloud-covered atmosphere may produce features too subtle for current instruments to resolve. You understand that Webb can identify major molecules in favorable cases, but faint or highly variable atmospheres may remain partially hidden. Even non-detections provide information, setting upper limits on molecular abundance and atmospheric density. Temperature also affects infrared observations. Planets close to their stars emit more thermal radiation, which can overwhelm or mask subtle spectral features. Conversely, cooler planets emit less infrared light, making absorption lines faint. By carefully selecting observing wavelengths, astronomers can optimize detection, emphasizing regions where specific molecules produce strong absorption. You notice that understanding the physical environment of a planet guides the choice of observational strategy, ensuring that collected data is scientifically meaningful. Instrument sensitivity is another factor. Webb's near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument MIRI are finely tuned to detect specific wavelengths with high resolution. Tiny detector noise, cosmic ray impacts, and thermal variations must be accounted for through calibration and data reduction. You realize that each photon must be correctly attributed, and that the smallest systematic errors can obscure subtle atmospheric signals. The process is deliberate and exacting, emphasizing methodical observation over dramatic effect. You consider the geometry of the system. Transit spectroscopy requires that the orbital plane aligns closely with your line of sight. Only a small fraction of planets meet this criterion, yet those that do provide a wealth of information. For non-transiting planets, direct imaging or reflected light studies are possible but more challenging. The contrast between the bright host star and the faint planetary signal must be carefully managed. Webb uses coronagraphs to block the starlight, allowing the much fainter light from the planet to be analyzed. You notice that even in these cases, detection is a careful subtraction of signals rather than a direct, obvious image. Atmospheric composition also introduces complexity. Molecules interact with light differently depending on temperature, pressure, and altitude. Water vapor produces absorption bands in specific infrared regions, while carbon dioxide and methane appear elsewhere. Clouds or hazes can obscure features, creating a flatter spectrum that hides underlying molecules. You understand that interpreting the data requires models that account for physical conditions and chemical reactions. These models are grounded in laboratory measurements and physics, providing a rigorous framework for understanding the observed spectra. Time is another subtle factor. Stellar variability, rotation, and activity can introduce fluctuations in light that mimic or obscure planetary signals. Red dwarfs like Proxima Centauri produce flares that alter the star's output across infrared and visible wavelengths. Webb observations must consider these effects, either by timing transits carefully or by modeling stellar variability. You notice that separating planetary signals from stellar noise is a careful process, one that relies on understanding the physics of both stars and planets. You think about the limits of molecular detection. Large molecules or those with weak absorption features may remain undetectable, while abundant gases produce clear, measurable signatures. Even within detectable ranges, precision depends on signal-to-noise ratio, exposure time, and repeated observations. By integrating data across multiple transits and combining measurements from different instruments, astronomers gradually build a more complete picture. Patience and repetition are essential. The universe does not yield its secrets instantly, but consistently when observed carefully. You reflect on the process of confirming results. Each detection is cross-checked against models, laboratory spectra, and observations of similar systems. Systematic errors are accounted for, and uncertainties quantified. Even subtle inconsistencies provide valuable feedback, guiding refinements in instrument calibration, observational strategy, and interpretation. You feel the slow, deliberate rhythm of science, where accuracy is paramount and clarity emerges from careful accumulation of evidence. The telescope's infrared coverage allows you to detect thermal emission from planets themselves. Hot planets emit more infrared light, providing information about surface or atmospheric temperature. Cooler planets emit less, but absorption features can still be measured with long exposures. You notice that the balance between thermal emission and absorption determines the strength of observable features. Understanding this balance is essential for interpreting spectra correctly. You consider how Webb contributes to broader scientific goals. Detecting water vapor, carbon dioxide, and methane informs your understanding of planetary formation, atmospheric chemistry, and potential habitability. Even when planets are too hot, too small, or too cloudy for complete characterization, upper limits on molecular abundance refine your models. Each observation, whether a clear detection or a constraint, adds to a growing understanding of planetary systems. Noise reduction and data processing are fundamental to observation. Raw data contains contributions from the telescope, detectors, cosmic rays, and background stars. Calibration, subtraction, and modeling remove these artifacts, leaving only the signal from the star-planet system. You notice that this careful preparation transforms faint variations in light into meaningful physical measurements. Observation is a process of patient refinement, where each step ensures that the resulting knowledge is accurate and reproducible. You realize that James Webb's observations are neither dramatic nor instantaneous. Each measured absorption line represents thousands of photons collected over hours, carefully processed to remove noise and instrumental effects. Even the faintest hints of water or methane are extracted through meticulous work rather than serendipity. You feel a quiet confidence in the rigor of these methods, knowing that every detection is supported by precise, repeatable science. You reflect on the balance between what can be seen and what cannot. Some atmospheric components remain beyond reach, while others are revealed clearly. Clouds, hazes, and stellar variability impose limits, yet careful planning, wavelength selection, and repeated measurements maximize what is observable. You notice that these limitations do not diminish knowledge. They define it, providing clear parameters for what can be inferred with confidence. Even in cases where planets cannot be fully characterized, upper limits on atmospheric composition are informative. You understand that knowing a planet lacks detectable water or has a thin atmosphere is a meaningful constraint. Observational limits guide future studies, refine models, and inform priorities for subsequent telescopes and instruments. Each photon, each measurement, contributes to a growing framework of evidence. You rest with the understanding that James Webb measures, rather than imagines. Its instruments detect photons, analyze spectra, and quantify features, all guided by physical principles. Observing exoplanet atmospheres is a patient, deliberate process, reliant on stability, calibration, and repeated measurement. Even faint signals provide valuable information, and every carefully measured absorption line contributes to the broader understanding of planetary environments. The signals from exoplanets, subtle and precise, reveal the composition, temperature, and structure of distant atmospheres. You notice that careful observation allows you to distinguish between stars, planets, and background noise, producing reliable information. This understanding sets the stage for considering how these atmospheres interact with stellar activity, surface conditions, and potential signs of habitability. You consider what it means for a planet to be habitable. It is not a guarantee of life, nor even of comfort. Habitability is a statistical assessment based on factors that make a planet capable of maintaining liquid water and a stable atmosphere over geological timescales. Around Alpha Centauri, these factors are influenced by stellar properties, orbital dynamics, and environmental conditions. Each element must be quantified carefully, as even small deviations can change a planet's prospects significantly. The first consideration is the habitable zone, defined as the range of distances from a star where surface temperatures allow liquid water to persist. Alpha Centauri A and B, being sun-like stars, have zones similar in concept to Earth's orbit, yet slightly adjusted for luminosity differences. Proxima Centauri, a cooler red dwarf, has a much closer habitable zone due to its lower energy output. You note that while a planet may orbit within this zone, it is not automatically habitable. Other conditions play an equally important role. Temperature alone is not sufficient. You examine how stellar flux fluctuates due to orbital eccentricity. A planet with an elliptical orbit experiences varying insolation, leading to periods of heating and cooling. If temperature swings are too extreme, atmospheric stability may be compromised. You understand that models account for these variations, simulating climate cycles based on orbital parameters and energy received from the host star. Habitability is thus a function of both average energy and the amplitude of variation over an orbit. Atmospheric composition is another key factor. Greenhouse gases such as carbon dioxide, methane, and water vapor help regulate surface temperatures, preventing runaway freezing or overheating. However, the balance is delicate. Too little greenhouse effect, and liquid water cannot persist. Too much and temperatures rise to extremes. Stellar radiation, particularly in the ultraviolet range, can alter chemical balances in the atmosphere, creating or destroying molecules that regulate climate. You notice that maintaining a stable atmosphere requires more than distance from the star. It requires chemical equilibrium, replenishment processes, and shielding from energetic radiation. You examine radiation exposure in more detail. Planets orbiting Proxima Centauri, or even Alpha Centauri A and B at closer distances, face levels of ultraviolet and X-ray radiation that vary with stellar activity. Magnetic fields, like Earth's, help deflect charged particles, preserving the atmosphere. Without a strong field, radiation can strip away lighter gases over time. You follow the physics patiently, noting that proximity to the star amplifies these effects. Even within a nominally habitable zone, a planet's survival depends on its ability to maintain magnetic protection. Orbital stability is a critical yet often overlooked factor. Alpha Centauri A and B orbit each other with a period of about 79 years, creating gravitational perturbations for any planets in their vicinity. You understand that stable planetary orbits must avoid resonance or extreme eccentricity induced by these stellar interactions. Around Proxima Centauri, orbiting far from the primary pair, stability is less affected, but tidal interactions may influence planetary rotation. Habitability models incorporate these dynamics to determine whether a planet can remain in a consistent orbit for billions of years, providing conditions conducive to maintaining an atmosphere and surface water. Tidal locking is a particular concern for planets around Proxima Centauri. Being close to the star, A planet may rotate slowly enough that one hemisphere faces the star continuously. You notice that this affects temperature distribution, atmospheric circulation, and potential habitability. Models suggest that thick atmospheres or efficient heat transfer can mitigate extreme temperature differences between the day and night sides. But these solutions depend on specific atmospheric composition and pressure. Habitability is therefore conditional, requiring a combination of orbital, thermal, and atmospheric stability. Planetary mass and size also play a role. Smaller planets have weaker gravity, which can limit their ability to retain an atmosphere over geological timescales. Larger planets retain atmospheres more effectively, but may experience higher internal heat, influencing tectonics and surface conditions. You notice that planetary density informs surface gravity, tectonic activity, and magnetic field generation, each contributing to habitability. Understanding these factors requires precise measurement of mass, radius, and orbital parameters, all of which can be inferred from light curves, radial velocity, and transit observations. You reflect on the cumulative effect of these constraints. Being in the habitable zone is necessary but not sufficient. Even planets at the correct distance may experience atmospheric loss, tidal locking, or climate instability. Conversely, planets slightly outside the zone could maintain habitability if other conditions compensate, such as a thick atmosphere or strong greenhouse effect. Habitability is statistical, not binary. It is about probability distributions, risk factors, and combined effects rather than a single criterion. Stellar variability introduces additional complexity. Flare frequency, intensity, and spectral distribution influence the persistence of atmospheric molecules. For red dwarfs, flare activity can remove ozone or water, while for sun-like stars, activity cycles modulate ultraviolet exposure. Habitability models account for these variations, quantifying the likelihood that a planet's atmosphere can survive over millions or billions of years. You perceive that stability, more than raw energy or luminosity, dictates a planet's prospects. You consider the role of planetary geology. Plate tectonics, volcanism, and internal heat flow recycle carbon and other volatile compounds, regulating climate over long timescales. Without geological activity, atmospheres can stagnate or collapse. Magnetic fields, maintained by internal dynamo processes, protect the atmosphere from solar wind. Habitability emerges from the interplay of stellar input, orbital dynamics, atmospheric chemistry, and internal planetary processes. Each factor is measurable, predictable, and grounded in physics. Water availability is influenced by multiple factors. Beyond temperature and atmospheric retention, water may be delivered during planet formation or lost to space through photodissociation. Stellar radiation, particularly in high-energy wavelengths, can split water molecules, allowing hydrogen to escape. Models simulate these processes, quantifying potential water retention. You notice that even small differences in planetary mass, atmosphere, or magnetic field strength significantly alter the outcome. Habitability depends on a delicate balance of these measurable parameters. The concept of a continuously habitable zone emphasizes temporal stability. A planet may enter the habitable zone early in its history, but stellar evolution can alter energy output over billions of years. Alpha Centauri A and B will gradually brighten, while Proxima Centauri remains stable over trillions of years. Models account for these long-term changes, simulating how temperature and radiation conditions evolve. You notice that habitability is thus a dynamic, time-dependent property, not a fixed location in space. You reflect on the statistical nature of habitability. Each factor, temperature, radiation, orbital stability, planetary mass, magnetic field, atmospheric composition, modifies the probability that a planet can maintain conditions suitable for liquid water. No single criterion is decisive. The combination of factors matters most. Even for nearby, sun-like stars, the likelihood of a planet meeting all requirements may be small. Habitability is not hope, but measurable probability based on well-established physics and observational data. You follow how these models influence observational strategies. Webb and other telescopes prioritize planets in stable orbits with favorable distances and masses. Spectral measurements of atmosphere, stellar activity, and orbital motion provide data to refine habitability assessments. Each observation contributes to a growing dataset that quantifies how often planets meet the conditions necessary for liquid water and stable atmospheres. You sense the deliberate, patient accumulation of evidence that defines modern exoplanet science. You consider how habitability interacts with detection limits. Webb can measure atmospheric molecules, stellar flux, and orbital parameters with precision, yet cannot directly observe surface conditions. Statistical models integrate these measurements, providing the best possible assessment of habitability. You notice that observational constraints are factored rigorously into probability estimates, rather than being ignored or idealized. Habitability remains a quantitative, scientific prediction, grounded in measurable factors. You rest with the understanding that proximity to a star does not guarantee safety or comfort. A planet may reside within the habitable zone and still be uninhabitable due to radiation, tidal forces, or atmospheric loss. Conversely, planets outside the nominal zone may sustain life under favorable conditions. Habitability is not a promise, but a measure of likelihood, based on temperature, radiation, orbit, atmosphere, and planetary structure. You perceive the quiet rigor of this science, free from speculation, yet rich with insight. Through careful observation, modeling, and analysis, you learn that Alpha Centauri provides a laboratory for understanding the limits of habitability. Even nearby stars, bright and seemingly familiar, impose constraints that must be quantified. Each measurement, each model, contributes to a cumulative understanding that guides expectations and informs exploration. You notice that probability and physics, not hope, define the boundaries of habitability. Even in the most favorable scenarios, planetary survival depends on a combination of distance, radiation shielding, orbital stability, and atmospheric resilience. Observations provide the data, while physics defines the constraints. You sense that habitability is an emergent property, arising from multiple interacting systems, each measurable and predictable. The probability of sustaining life-supporting conditions is finite and calculable, reflecting a universe that is orderly and comprehensible when approached systematically. You allow your mind to settle with this measured understanding. Habitability is conditional, constrained, and statistical. The limits imposed by stellar radiation, orbital mechanics, planetary mass, and atmospheric chemistry are not discouraging. They are precise, predictable, and observable. Alpha Centauri offers a nearby case study, illustrating that even sun-like stars require planets to meet multiple conditions to remain suitable for liquid water and atmospheric stability. You turn your focus to the ways a star actively influences the planets around it. Even within a habitable zone, planets are subject to stresses from their host star. Stellar flares, winds, and ultraviolet radiation constantly shape atmospheric chemistry, surface conditions, and the ability to retain volatile molecules. These forces act quietly but persistently, testing whether a planet can maintain conditions favorable for long-term stability. Flares are among the most visible forms of stellar activity. On red dwarfs like Proxima Centauri, flares can temporarily increase a star's brightness by orders of magnitude, especially in ultraviolet and X-ray wavelengths. You note that these energetic bursts release charged particles that move outward through the planetary system at high speed. A planet without a magnetic field may experience significant atmospheric erosion as lighter molecules, particularly hydrogen, escape into space. Webb's infrared observations allow scientists to track the effects of these flares on circumstellar environments, revealing subtle signatures of energy absorption and emission. Stellar winds present a continuous influence, exerting pressure on planetary atmospheres. Unlike flares, winds are steady streams of charged particles emitted by a star. Their effect is cumulative over millions of years, slowly stripping lighter gases from a planet's atmosphere. You consider how this process is analogous to the slow evaporation of a liquid, measurable over time but imperceptible moment to moment. The strength of the stellar wind depends on the star's magnetic activity and rotation rate, and in young, rapidly rotating stars, winds can be intense enough to reshape planetary atmospheres. Ultraviolet radiation, though less visually dramatic than flares, contributes to chemical changes in atmospheres. UV photons break molecular bonds, dissociating water and other compounds. Hydrogen may escape, while oxygen or other heavier molecules remain. Over time, this alters the composition and density of an atmosphere. You notice that Webb cannot directly detect every escaping atom, but infrared measurements of thermal signatures and molecular absorption provide indirect evidence of long-term atmospheric evolution. These observations allow models to quantify the cumulative effect of UV exposure over billions of years. You consider the protective role of planetary magnetic fields. A planet with a strong Earth-like magnetic field can deflect charged particles from flares and stellar winds, preserving its atmosphere. Magnetic fields are generated by internal dynamo processes, dependent on rotation, core composition, and convective activity. Without this shield, even planets in the habitable zone may gradually lose atmosphere, decreasing the probability of maintaining liquid water or stable surface conditions. You notice that habitability is not simply about distance from the star. It requires the combination of protective mechanisms and favorable external conditions. Infrared data from Webb contributes to understanding these processes. By monitoring thermal emissions and spectral features, astronomers can detect fluctuations caused by stellar activity. Variations in atmospheric temperature or the presence of certain molecules indicate how a planet responds to bursts of high-energy radiation. Over multiple observations, these data build a detailed record of atmospheric resilience, highlighting whether a planet can absorb, redistribute, or survive the stresses imposed by its star. You feel the patience embedded in these measurements, revealing gradual changes rather than dramatic events. Planetary rotation interacts with stellar activity to influence habitability. Tidal locking around red dwarfs results in a fixed day and night side. The constant bombardment of one hemisphere by stellar winds and radiation requires efficient heat transfer through the atmosphere to maintain habitable conditions. Models suggest that planets with sufficient atmospheric pressure or circulation can redistribute energy, mitigating extremes. You notice that even minor differences in rotation, tilt, or atmospheric composition can dramatically affect how a planet withstands stellar stress. Cumulative effects over time are critical. Short-lived flares may not significantly erode an atmosphere, but millions of years of repeated exposure can cause measurable loss of hydrogen, oxygen, and other volatile elements. You consider how atmospheric erosion models integrate stellar activity, magnetic shielding, and planetary composition to estimate the likelihood of long-term survival. Webb's ability to observe thermal signatures and molecular abundances allows astronomers to test these models against real systems, refining predictions about the endurance of planetary atmospheres. You think about comparative cases in our own solar system. Venus, Mars, and Earth experience different degrees of atmospheric loss due to solar wind and radiation. Mars, with a weak magnetic field and low gravity, lost much of its original atmosphere over billions of years. Venus, with a thick atmosphere and slow rotation, retains heat and gases despite high solar flux. Earth, protected by a magnetic field and stable orbit, maintains a delicate balance. These examples help quantify the ways in which stellar activity shapes atmospheres and guide expectations for planets in Alpha Centauri. Planetary mass and gravity are also factors. Heavier planets retain atmospheres more effectively under stellar stress. Lighter planets, especially those with high exposure to flares or stellar winds, are more vulnerable to gradual erosion. Even small differences in mass, composition, or orbital distance can change the cumulative effect of stellar activity. You notice that these parameters can be measured or inferred from transit timing, radial velocity, and spectral analysis, providing the quantitative foundation for understanding habitability limits. You reflect on how models combine multiple forms of stellar stress. Flares, winds, UV radiation, and tidal effects are considered together to predict atmospheric evolution. Webb's observations provide critical constraints by measuring spectral lines and thermal emissions, allowing scientists to quantify the degree of erosion, molecular changes, and potential habitability over time. Each data point informs simulations that extend billions of years into the future, connecting instantaneous observations to long-term outcomes. You perceive the slow, deliberate accumulation of evidence, producing reliable understanding. Stellar variability also acts as a natural stress test. Even sun-like stars undergo cycles of activity that subtly modulate radiation and wind strength. These cycles influence atmospheric chemistry and temperature over decades to centuries. By studying these cycles, you learn how predictable fluctuations interact with stochastic events like flares. Webb's infrared observations provide the precision to detect small but meaningful variations in planetary energy absorption, helping to determine whether an atmosphere can maintain long-term stability. You consider the indirect effects of stellar activity on potential habitability. Surface conditions, climate regulation, and chemical cycles all depend on the balance between incoming energy, radiation exposure, and atmospheric retention. A planet may lie in the habitable zone yet fail to sustain conditions suitable for life if cumulative stellar stress exceeds its protective capacity. You notice that this understanding arises not from speculation, but from combining physics, chemistry, and long-term observational data into models that quantify planetary resilience. You reflect on the quiet, cumulative nature of this testing. Unlike dramatic collisions or eruptions, stellar stress is continuous, subtle, and methodical. Atmospheric changes occur over millions of years, yet they are measurable, predictable, and comprehensible. Each flare, wind stream, or ultraviolet burst adds incrementally to a planet's history, shaping what it may become. You appreciate the patient rhythm of this science, where time, observation, and modeling converge to reveal a planet's capacity to survive its star's influence. Planetary habitability emerges as a balance between external stressors and internal protections. Magnetic fields, atmospheric density, rotation, and composition interact with stellar flares, winds, and radiation to determine long-term viability. Webb's infrared measurements provide the data necessary to evaluate these interactions. Each observation, carefully processed and analyzed, contributes to a probabilistic understanding of how planets withstand the stresses imposed by their host stars. You rest with the awareness that stability matters more than luminosity. A bright star may provide energy, but repeated flares, strong winds, or high UV flux can erode a planet's atmosphere and compromise habitability. Conversely, a star with moderate energy output but low variability allows a planet to maintain conditions for long durations. Stellar activity is the ultimate test, measured in photons, particles, and cumulative impact rather than drama or spectacle. Through observation and modeling, you recognize that planets are constantly being evaluated by their stars. Stellar activity acts as a stress test, shaping atmospheres, regulating chemistry, and influencing temperature. You notice that habitability depends not only on distance and energy, but on the planet's ability to endure these ongoing, measurable challenges. Each flare and wind stream is a subtle probe, revealing the resilience of planetary systems over geological time. You consider the language of scientific observation. When scientists describe a result as disturbing, the meaning is precise, detached from emotion. It does not imply fear or alarm. It signals that an observation differs from prior expectations or models. A disturbing result is one that challenges assumptions, requiring careful reevaluation of existing understanding. You notice that this usage is entirely factual, rooted in evidence rather than opinion. In the context of Alpha Centauri and its planets, Webb's observations have revealed features that differ subtly from prior predictions. Some atmospheric compositions, stellar activity levels, or orbital dynamics are not what models anticipated. You understand that this discrepancy does not negate prior knowledge. It simply refines it, highlighting areas where earlier assumptions were incomplete. Each disturbing finding becomes an opportunity to improve understanding. Scientific expectations are based on models, which are mathematical representations of physical processes. Models incorporate current knowledge, including stellar physics, planetary formation theories, and atmospheric chemistry. You realize that no model perfectly predicts reality, because natural systems contain complexity and variation. When a measurement deviates from model predictions, it is considered disturbing in the sense that it demands a reassessment of assumptions. The word is a tool for precision, signaling the need for recalibration rather than alarm. You notice that the James Webb Space Telescope produces data with high accuracy and resolution. Infrared spectroscopy, thermal measurements, and precise light curves provide new insight into planetary and stellar systems. Occasionally, these observations reveal unexpected molecular abundances, subtle variations in stellar flux, or differences in orbital behavior. Each unexpected result is labeled scientifically as disturbing because it contradicts prior expectations, yet every finding is fully consistent with physical laws. The term expresses the need to adjust understanding, not to evoke concern. In this context, disturbing results highlight the limits of prior models rather than the limits of knowledge. For example, a planet in a nominal habitable zone may show signs of atmospheric erosion inconsistent with simple estimates of stellar radiation. The discrepancy does not indicate failure. It shows that additional factors, such as magnetic shielding, flare frequency, or orbital dynamics, must be incorporated. You perceive that the adjustment process is iterative, refining models in response to precise observations. You reflect on the contrast between expectation and observation. Before Webb, scientists projected potential compositions for planets in Alpha Centauri based on stellar type, age, and distance. These projections were plausible and internally consistent, but they relied on approximations and assumptions. Webb's data, collected in infrared wavelengths with unprecedented sensitivity, sometimes reveals deviations. These deviations are the scientific equivalent of a gentle nudge, encouraging reevaluation and refinement. They are not dramatic surprises. They are measurable refinements of understanding. The term disturbing also underscores the predictive nature of science. By establishing expectations through models, scientists can test hypotheses against real data. When observations differ, the discrepancy quantifies what is missing or misunderstood. You notice that the word is a signal of learning, emphasizing the process of inquiry rather than the results themselves. Each unexpected measurement becomes a focus for investigation, allowing the scientific community to converge on more accurate representations of reality. You consider how this applies to habitability studies. Models of Alpha Centauri's planetary environments suggested certain atmospheric compositions and stability ranges. Webb's infrared spectra occasionally detect variations, unexpected molecular abundances, or subtle deviations in temperature profiles. These findings are termed disturbing because they challenge simplified expectations, yet they provide precise, actionable information. They guide refinements in planetary climate models, stellar activity estimates, and long-term habitability predictions. You notice that the process is constructive, enhancing understanding without speculation. Scientific language is intentionally restrained. Using words like disturbing allows researchers to communicate deviations objectively, without implying drama. The term conveys that data requires reevaluation while remaining consistent with the underlying principles of physics, chemistry, and astronomy. You appreciate that this precision avoids exaggeration and ensures that interpretations remain grounded in evidence. Observers and modelers alike can focus on measurable discrepancies rather than narrative or emotional framing. Webb's measurements, when labeled disturbing, also highlight the importance of uncertainty. Every observation carries statistical and systematic uncertainties, which are quantified carefully. Deviations from expected results are interpreted within these uncertainty ranges. If a measurement falls outside predicted confidence intervals, it is scientifically disturbing, prompting a careful reanalysis. You notice that this rigorous approach ensures that conclusions are evidence-based, probabilistic, and reproducible, rather than speculative. You reflect on how disturbing results contribute to the growth of scientific knowledge. Each deviation refines models of stellar activity, atmospheric retention, or planetary climate. Webb's observations provide data points that reduce uncertainty, improve predictive power, and guide future observations. The term does not imply alarm. It signals an opportunity to update understanding based on precise, verifiable measurements. You notice the iterative rhythm of science. Observe, compare, adjust, and repeat. You consider the balance between expectation and discovery. Prior optimism about habitable planets or stable atmospheres is tempered by refined observations. Some assumptions are challenged, while others are confirmed. Disturbing results narrow possibilities, guiding focus toward realistic conditions rather than hopeful speculation. You appreciate that science advances not by expanding imagination, but by progressively constraining reality through measurement, analysis, and modeling. In the context of Alpha Centauri, each disturbing result helps define what is physically possible for nearby planetary systems. Webb's precise infrared data allows detection of subtle variations in atmosphere, temperature, and orbital behavior. When predictions do not align perfectly with these observations, scientists do not interpret this as failure. They recognize it as refinement. You notice that each adjustment moves understanding closer to a model consistent with measurable, reproducible phenomena. You rest with the understanding that the word disturbing in science is a tool for clarity. It identifies results that challenge prior expectations while remaining entirely grounded in evidence. It signals opportunity for learning and model improvement, rather than alarm or uncertainty. You notice that in practice, these results guide further observations, refine predictive models, and support a deeper understanding of the conditions in and around Alpha Centauri. Observing how expectations are tested and refined teaches a quiet lesson. Scientific progress relies on noticing deviations, quantifying them, and updating understanding. Each disturbing observation is a step toward a more accurate representation of reality. Webb's findings, subtle yet measurable, exemplify this approach, providing evidence that advances knowledge without speculation or exaggeration. You allow your mind to settle with this clarity. Deviations from expectation are not surprises. They are guides. They highlight areas for adjustment, quantify limitations, and refine the boundaries of what is known. You notice that scientific language, precise and careful, supports comprehension, measurement, and rational interpretation. Each observation, each refinement, is part of the steady accumulation of understanding. You begin by observing the Alpha Centauri system with careful attention to measurable properties. It is a triple-star system, composed of Alpha Centauri A, B, and the distant red dwarf Proxima Centauri. Alpha Centauri A is slightly more massive and luminous than the Sun, while Alpha Centauri B is slightly less massive and cooler. Proxima Centauri, much smaller and dimmer, orbits at a distance of roughly 0.2 light-years from the primary pair. Each star presents distinct gravitational, radiative, and dynamical environments, influencing the potential for stable planetary systems. Comparing this to our solar system, you notice a contrast in simplicity and stability. The Sun, a single star, provides a consistent gravitational center around which planets orbit with minimal perturbation. Alpha Centauri A and B, orbiting each other every 79 years, create a gravitationally dynamic environment that affects any nearby planets. Planets around the primary pair must maintain precise orbits to avoid destabilizing interactions. In contrast, Earth experiences only the minor influences of distant planets and Jupiter's gravitational field, contributing to its long-term orbital stability. You examine radiation output. Alpha Centauri A, slightly more luminous than the Sun, emits more energy, affecting the location of its habitable zone. Alpha Centauri B emits less, requiring closer orbits for similar temperatures. Proxima Centauri's habitable zone is very close to the star due to its low luminosity, increasing the potential for tidal locking and exposure to stellar activity. In comparison, the Sun provides a habitable zone at a comfortable distance, and Earth's rotation and atmosphere distribute energy efficiently. You notice that stability and predictability in stellar output contribute significantly to the long-term persistence of planetary environments. Orbital dynamics differ markedly between the systems. In the solar system, planets follow near-circular orbits, minimizing temperature extremes and orbital eccentricity effects. The gravitational influence of Jupiter and Saturn creates small, measurable perturbations, but these are consistent and predictable. In Alpha Centauri, the gravitational interaction between the two primary stars introduces potential oscillations in planetary orbits. Simulations indicate that only certain orbital radii allow planets to remain stable over billions of years. You realize that the architecture of the stellar system constrains where long-term habitable planets can exist. Planetary formation theories help you understand why these differences matter. Planets form from protoplanetary disks of gas and dust orbiting young stars. In a multi-star system, disk dynamics are influenced by the combined gravitational forces of the stars. Material may be perturbed or truncated, affecting planet size, mass, and composition. Around Alpha Centauri A and B, disks may be disrupted by the companion star, reducing the likelihood of forming Earth-sized planets at ideal distances. The Sun, solitary and stable, allowed the solar system's planets to form without significant external gravitational interference. You perceive that the formation environment plays a critical role in determining the number, type, and stability of planets. You consider the implications for habitability. Even if a planet forms within the habitable zone, gravitational perturbations can alter its orbit over millions of years. Alpha Centauri's binary nature introduces variability in orbital eccentricity and tilt, which affects climate stability. Proxima Centauri's proximity to the primary pair is distant enough to minimize orbital disruption, but its stellar activity imposes different challenges. You notice that Earth's consistent orbital parameters and moderate stellar output provide unusually favorable conditions for maintaining a stable climate and atmosphere over geological time. Comparing planetary masses and densities, you see that Earth-sized planets are common in simulations of Alpha Centauri's habitable zones, yet their survival depends on precise orbital conditions. Smaller planets may struggle to retain atmospheres in the face of stellar winds or flares, while larger planets may retain atmospheres but develop climates unsuitable for surface liquid water. The solar system illustrates how mass, distance, and composition combine with stellar stability to create a finely tuned balance. You perceive that such balance may be uncommon even around sun-like stars. You examine radiation and spectral output in more detail. Alpha Centauri A emits slightly more ultraviolet radiation than the Sun, while B emits slightly less. The combined effect on potential atmospheres is complex, requiring models of atmospheric retention, molecular dissociation, and photochemistry. Proxima Centauri's flare activity introduces high-energy bursts that can strip atmospheres over time. In the solar system, the Sun's moderate ultraviolet output and the presence of Earth's magnetic field and ozone layer provide protection and stability. You realize that habitability is not simply a function of distance from a star, but of the interplay between radiation, atmosphere, and magnetic shielding. Tidal effects also differ between the systems. Close-in planets around Proxima Centauri are likely to be tidally locked, with one hemisphere continuously facing the star. This affects temperature gradients, atmospheric circulation, and the distribution of liquid water. In contrast, Earth's rotation period and distance from the Sun create diurnal cycles that moderate climate and prevent extreme temperature disparities. You notice that stellar configuration strongly influences planetary rotation and climate, further affecting long-term habitability. You reflect on comparative planetary geology. Plate tectonics, volcanism, and magnetic field generation depend on mass, internal heat, and rotational dynamics. Planets forming around Alpha Centauri may have similar internal structures, but the long-term evolution of their magnetic fields and tectonics is sensitive to orbital dynamics and tidal forces. In our solar system, Earth's rotation and internal heat have maintained a magnetic field and tectonic activity for billions of years, contributing to atmospheric retention and surface habitability. You sense that these processes are interconnected, emphasizing that small differences in system architecture can have profound consequences. The stability of orbital planes is another point of comparison. In Alpha Centauri, the interaction between the two primary stars creates precession and small oscillations that can alter orbital inclinations over time. These changes affect climate cycles, seasonal variability, and the potential for long-term water retention. In the solar system, orbital inclinations are relatively stable, allowing predictable seasons and minimal long-term perturbations. You notice that the combination of stellar mass, distance, and configuration plays a decisive role in planetary stability. You consider the statistical implications. Even though Sun-like stars are common, the particular combination of stellar output, orbital stability, magnetic shielding, and planetary formation conditions that enabled Earth to remain habitable for billions of years may be rare. Alpha Centauri demonstrates that proximity and similarity of stellar type do not guarantee Earth-like conditions. Habitability depends on a precise balance of multiple factors, all measurable and constrained by physics. You reflect that familiar worlds are exceptional not because the stars are rare, but because the combination of circumstances producing stable planets is uncommon. Finally, you appreciate the value of comparative study. By examining Alpha Centauri in relation to the solar system, you quantify how differences in mass, luminosity, orbital dynamics, and formation processes influence potential habitability. Webb's observations provide data that test models, refine predictions, and highlight the constraints on planetary survival. You notice that each measured parameter, each spectral feature, and each orbital determination contributes to a clearer understanding of the factors that enable long-term stability in planetary systems. You rest with the quiet recognition that common stars do not guarantee familiar worlds. Alpha Centauri's multiple stellar dynamics, radiation output, and potential for planetary perturbation illustrate how delicate the balance of habitability can be. Even small differences in stellar mass, orbital eccentricity, or radiation levels may produce worlds very different from Earth. Observing these contrasts provides perspective, highlighting the precise conditions that allowed Earth's long-term stability and deepening your appreciation for the measurable, constrained parameters that define life-supporting planets. You begin by contemplating the scale of planetary history. Time for a planet is measured in billions of years, far exceeding human perception. Each planetary surface, atmosphere, and magnetic field has been shaped by processes that unfold slowly and consistently. Survival is not instantaneous. It requires persistence across epochs, with resilience to both internal and external forces. You notice that the passage of time tests every aspect of a planet, from its crust to its upper atmosphere. Atmospheric retention is one of the most time-dependent processes. Over millions or billions of years, stellar radiation, particle flux, and chemical reactions gradually alter atmospheric composition. Light molecules, such as hydrogen, may escape into space, while heavier molecules remain. You observe that planets with weak gravity or no magnetic field are especially vulnerable. Earth's atmosphere has persisted due to a combination of gravity, magnetic shielding, and active replenishment through volcanic outgassing and biological processes. The stability of these mechanisms over time is critical for long-term habitability. Magnetic fields play a central role in planetary endurance. Generated by the motion of conductive material in a planet's core, magnetic fields deflect charged particles from the host star, reducing atmospheric loss. Without this protective shield, slow erosion from stellar winds and flares can dramatically alter atmospheric density and composition. Over billions of years, even moderate stellar activity can remove significant quantities of gas. You understand that a planet's survival depends on its ability to sustain these protective mechanisms over geological timescales. Geological recycling contributes quietly but persistently to planetary survival. Plate tectonics, volcanism, and mantle convection redistribute heat, recycle carbon, and stabilize surface conditions. Volcanic activity releases gases into the atmosphere, replenishing what has been lost to space, while tectonic movement prevents stagnation and maintains long-term chemical equilibrium. These processes operate over millions of years, providing a stabilizing influence that allows climate and surface conditions to remain within habitable ranges. You notice that time is as much a shaping force as any star or planet property. You consider stellar aging and its effect on planetary conditions. Stars gradually change their luminosity, temperature, and activity levels over billions of years. Alpha Centauri A and B will slowly brighten, increasing radiation output and shifting the habitable zone outward. Proxima Centauri, a red dwarf, will remain relatively stable, but flare activity can continue for trillions of years. Planets must survive not just formation, but the evolving conditions imposed by their stars. You perceive that long-term habitability requires alignment between planetary resilience and stellar behavior over immense spans of time. Climate regulation depends on the interaction of time-dependent processes. Slowly evolving factors such as orbital eccentricity, axial tilt, and precession influence seasonal and long-term climate cycles. Small changes, accumulated over millions of years, can alter surface temperature, ice coverage, and atmospheric circulation. Earth's relative stability is unusual, as small perturbations in orbital parameters can produce significant effects over geologic time. You notice that a planet's endurance is a product of both predictable cycles and buffering mechanisms that absorb or redistribute energy. Water retention illustrates the cumulative effect of time. Photodissociation, thermal escape, and chemical interactions gradually remove hydrogen and other light elements from the atmosphere. Geological activity can replenish water through volcanism or recycling of hydrated minerals. You understand that planets must maintain a balance between loss and replenishment, which unfolds incrementally over billions of years. A single moment in time cannot determine habitability. It is the persistence of conditions across epochs that matters. Tidal effects are influenced by long timescales as well. Gravitational interactions with a host star or neighboring planets slowly modify rotation rates, orbital eccentricity, and axial tilt. Over millions of years, these changes can affect climate stability, magnetic field generation, and atmospheric circulation. Planets in tightly bound systems, like Proxima Centauri's habitable zone, may experience tidal locking that evolves gradually. You notice that survival requires accommodation to these long-term shifts, allowing equilibrium to persist despite subtle dynamical changes. You reflect on the importance of cumulative energy input. Stellar radiation, cosmic rays, and internal heat gradually modify planetary conditions. The energy delivered over billions of years drives chemical reactions in the atmosphere, melts ice, circulates oceans, and supports tectonic activity. You perceive that time allows slow, consistent processes to define surface conditions, demonstrating that planetary survival is the outcome of sustained interactions rather than isolated events. Biological processes where present also operate across time. Microbial activity, photosynthesis, and carbon cycling gradually modify atmospheric composition and surface chemistry. Life itself becomes a stabilizing factor, but it requires resilience to both internal planetary changes and external stellar influences. You notice that persistence and feedback are central themes. A planet must endure and respond over geological timescales to remain favorable for habitability. Observational evidence confirms these time-dependent processes. Studies of Earth, Mars, Venus, and icy moons show how atmospheres and surfaces evolve over billions of years. Geologic records preserve evidence of gradual change, including climate cycles, magnetic reversals, and tectonic shifts. By comparing planets in our solar system to models of Alpha Centauri, you can quantify the cumulative effects of stellar radiation, orbital dynamics, and internal heat over time. This reinforces the principle that survival is a function of sustained conditions and adaptive processes. Planetary mass influences endurance subtly but continuously. Heavier planets retain atmospheres more effectively, resist thermal escape, and maintain internal heat longer. Smaller planets are more susceptible to gradual erosion of atmosphere and cooling of the core, which may extinguish magnetic fields. Over billions of years, these differences accumulate, producing measurable divergence in planetary environments. You notice that long-term habitability is probabilistic, emerging from the interaction of many measurable factors over immense timeframes. Time also moderates the consequences of stellar activity. Flares, winds, and ultraviolet radiation may strip small amounts of atmosphere during each event, but the total effect becomes significant only over millions of years. Similarly, tectonic recycling, volcanic replenishment, and magnetic shielding act consistently over the same timescales, counterbalancing loss. You perceive that planetary survival is not determined by any single event, but by the interplay of continuous, time-dependent processes. You consider Alpha Centauri's planets in this context. Even if a planet forms in the habitable zone, it must survive flares, orbital perturbations, and atmospheric erosion over billions of years. Only through persistence and resilience do conditions remain conducive to liquid water and stable climates. Time is the ultimate test, The combination of stellar, orbital, and planetary processes determines whether a world endures long enough to be truly habitable. You rest with the understanding that planetary survival is the product of slow, cumulative processes. Atmospheres evolve, surfaces recycle, magnetic fields persist or decay, and stars age, all over immense timescales. Endurance is not determined by a single moment of formation but by the ability to withstand the persistent forces of radiation, gravity, and internal dynamics. You notice that observing a planet in its present state captures only a snapshot. True habitability emerges from billions of years of measurable, consistent interaction. You begin by focusing on the earliest stages of planetary existence, long before planets have surfaces, atmospheres, or orbits that can be measured directly. Planet formation starts within disks of gas and dust that surround young stars. These protoplanetary disks are composed primarily of hydrogen and helium, with smaller amounts of heavier elements such as carbon, oxygen, silicon, and iron. Over time, these materials interact through gravity, collision, and accretion, slowly assembling into larger bodies. You notice that this process unfolds gradually, governed by well-tested physical laws rather than sudden events. James Webb's infrared sensitivity allows these disks to be studied with unprecedented clarity. Dust grains, too small to be seen in visible light, emit thermal radiation in infrared wavelengths. By measuring this radiation, Webb reveals the temperature, density, and composition of disk material. You observe that these measurements align closely with long-standing models of disk evolution, confirming that planets form through incremental growth rather than rapid collapse. The data reinforce the understanding that planet formation is a slow and orderly process. You consider how dust grains collide and stick together. Initially, microscopic particles bond through electrostatic forces, forming larger aggregates. As these aggregates grow, gravity becomes increasingly important, allowing kilometer-scale bodies called planetesimals to form. Webb's observations detect gaps and rings in protoplanetary disks, features predicted by models where growing planets clear paths through surrounding material. You recognize that these structures provide direct evidence of planet formation in progress, confirming theories developed decades earlier. Chemical composition is another area where Webb provides confirmation. Infrared spectroscopy reveals the presence of water vapor, carbon dioxide, methane, and complex organic molecules within disks. These compounds are distributed according to temperature gradients, with volatile substances forming farther from the star and more refractory materials remaining closer. You notice that this chemical stratification matches expectations from thermodynamic modeling. The placement of these materials influences the types of planets that form, shaping whether they become rocky worlds, gas giants, or ice-rich bodies. You reflect on the role of distance from the star. Close to the star, high temperatures prevent volatile compounds from condensing, favoring rocky planet formation. Farther out, ices and gases accumulate, enabling the formation of gas giants and icy planets. Webb's data confirm these temperature-dependent boundaries, often called frost lines, within observed disks. You understand that these boundaries are not rigid lines but gradual transitions, influenced by stellar luminosity and disk dynamics. Gravitational modeling also finds support in Webb's observations. The distribution of mass within disks, inferred from infrared emission, matches predictions from simulations of rotating, collapsing molecular clouds. These simulations show how angular momentum shapes disk structure and determines where material accumulates. You observe that Webb's measurements of disk mass and thickness agree with these models, confirming that gravity and conservation of angular momentum govern early planetary architecture. You think about the timescales involved. Disk lifetimes are typically a few million years, after which stellar radiation and winds disperse remaining gas and dust. Webb's observations of disks at different stages reveal a progression consistent with this timeline. Younger disks appear dense and gas-rich, while older disks show gaps, rings, and reduced material. This sequence supports the understanding that planet formation occurs relatively early in a star's life, constrained by the availability of disk material. You notice that Webb does not fundamentally alter theories of planet formation, but strengthens them. Previous telescopes provided indirect evidence and partial measurements, while Webb offers direct, high-resolution data. This allows astronomers to test predictions quantitatively, reducing uncertainty rather than introducing speculation. You recognize that this kind of confirmation is essential, transforming theoretical models into robust explanations supported by observation. You consider how this applies to Alpha Centauri, the system stars likely formed from the same molecular cloud, each with its own protoplanetary disk. Webb's findings suggest that disk evolution around these stars followed familiar patterns, shaped by gravity, temperature, and chemistry. The presence or absence of planets around each star depends on subtle differences in disk mass, lifetime, and stellar interaction. You understand that planet formation is sensitive to initial conditions, even when overall processes are universal. The presence of organic molecules within disks draws your attention. These molecules form through chemical reactions on dust grain surfaces and in gas phases, driven by radiation and temperature gradients. Webb's detection of such compounds confirms that the basic chemical ingredients for complex chemistry are widespread. You notice that this does not imply biological activity, but it establishes a consistent chemical foundation from which planetary atmospheres and surfaces can develop. You reflect on the importance of confirmation in science. Webb's observations validate decades of laboratory experiments, numerical simulations, and indirect measurements. This convergence strengthens confidence in existing frameworks, allowing scientists to focus on refining details rather than questioning fundamentals. You sense that this steady accumulation of evidence exemplifies the careful, cumulative nature of scientific progress. You think about uncertainties that remain. While Webb confirms many aspects of planet formation, it also highlights areas where models can be improved. Variations in disk turbulence, magnetic fields, and chemical pathways introduce complexity. However, these refinements occur within a well-established framework, not in opposition to it. You appreciate that science advances by narrowing possibilities, guided by increasingly precise observations. You consider how planet formation sets initial conditions for later habitability. The size, composition, and location of a planet determine its ability to retain an atmosphere, generate a magnetic field, and sustain geological activity. Webb's confirmation of formation processes allows these later stages to be modeled more accurately. You recognize that understanding beginnings is essential for interpreting present-day planetary environments. You observe that Webb's role is not to search for dramatic exceptions, but to measure reality with greater accuracy. Its infrared instruments reveal subtle details that either support or gently constrain existing ideas. In doing so, Webb demonstrates that progress often comes through verification rather than surprise. You feel a sense of quiet reassurance in this consistency. You reflect on how this confirmation influences expectations for nearby systems. Alpha Centauri's planets, if present, likely formed through the same processes observed elsewhere. Differences in stellar interaction and disk dynamics may affect outcomes, but the underlying physics remains consistent. You understand that familiarity in process does not guarantee similarity in result, yet it provides a reliable basis for comparison. You notice that the language of confirmation lacks drama, yet it carries deep significance. To confirm a theory means it has withstood careful testing against observation. Webb's data provides such tests, reinforcing confidence in planetary science. You appreciate that this strengthens the foundation upon which future discoveries will rest. You rest with the understanding that planet formation is neither mysterious nor chaotic. It is a gradual, measurable process shaped by gravity, chemistry, and time. Webb's observations affirm this view, offering clarity rather than revision. The early stages of planetary systems unfold predictably, even though their final outcomes may differ. As your attention settles, you recognize that understanding how planets form does not make them reachable. Distance remains a defining constraint, one governed by physics rather than curiosity, gently guiding your thoughts toward the vast separations that keep nearby stars observationally close but physically far. You begin by observing the scale of interstellar space. Alpha Centauri, only 4 light-years away, seems close in cosmic terms. Yet even at the speed of light, which is the universal speed limit, it would take more than 4 years for a signal or a spacecraft to arrive. You notice that human-made spacecraft travel far slower than this maximum, constrained by energy, mass, and propulsion technologies. The distance challenges intuition, requiring precise calculation to understand why proximity does not imply accessibility. Current spacecraft rely on chemical propulsion, nuclear power, or ion drives. Chemical rockets provide the thrust needed to escape Earth's gravity but quickly exhaust fuel and accelerate only briefly. Ion propulsion uses electrical energy to accelerate particles gradually, offering continuous low thrust over long periods. Each method demonstrates that achieving velocities even a fraction of light speed requires immense energy, carefully managed over time. You understand that reaching another star involves not only speed but the ability to sustain acceleration without depleting resources. Energy requirements dominate the challenge. Propelling a spacecraft to even 1/10 the speed of light requires energy comparable to the total annual consumption of a small nation. You consider mass carefully. The heavier the spacecraft, the more energy is required for acceleration. Adding shields, communication equipment, scientific instruments, and life support increases mass further. Even in an ideal vacuum, where friction is negligible, the energy needed grows dramatically with speed. You notice that these constraints limit practical interstellar missions to theoretical or near-future concepts. You reflect on the duration of travel. Even if a spacecraft could reach 10% of light speed, the journey to Alpha Centauri would take more than 40 years. For a fully human crew, this raises challenges of life support, radiation shielding, and psychological health over multiple decades. For unmanned probes, instruments must endure extreme cold, cosmic radiation, and decades of autonomous operation. You observe that these timescales are orders of magnitude longer than human lifespans or the operational lifetime of current spacecraft systems. Radiation exposure is another limiting factor. Interstellar space contains high-energy particles and cosmic rays that gradually damage materials and electronics. Prolonged exposure can degrade spacecraft components or disable instruments. Shielding adds mass, which in turn increases propulsion energy requirements. You notice that this creates a trade-off. More protection demands more energy, which is difficult to provide over decades of travel. Each design choice must be optimized within strict physical constraints. Even communication imposes limits. Signals travel at the speed of light, so a probe reaching Alpha Centauri would take over 4 years to send data back to Earth. Any real-time control is impossible. Autonomous operation becomes essential. You understand that planning, monitoring, and adjusting a mission require anticipation, careful engineering, and patience far beyond typical human experience. Distance dictates not only travel time but the flow of information. You consider hypothetical propulsion systems. Concepts such as laser-driven light sails, nuclear pulse propulsion, and antimatter drives suggest the possibility of higher velocities. Light sails use focused laser beams to push a low-mass spacecraft, potentially achieving a significant fraction of light speed. Nuclear pulse propulsion converts small nuclear explosions into thrust, while antimatter reactions release enormous energy per unit mass. Each approach remains limited by technological, financial, and safety constraints. You notice that while promising in theory, none yet provide a practical route to Alpha Centauri for large or crewed spacecraft. Time dilation, predicted by special relativity, offers a subtle effect at very high velocities. Approaching light speed, time aboard the spacecraft passes more slowly relative to Earth. While this could reduce subjective travel time for crew, it does not reduce the objective distance. You observe that even relativistic effects cannot overcome the fundamental limits imposed by energy, acceleration, and mass. Time dilation becomes significant only near light speed, which remains far beyond our current capabilities. You reflect on the logistics of sustaining a mission over decades. Power generation, thermal control, and maintenance all require resources or autonomous repair systems. Solar power diminishes rapidly with distance from the sun, while radioisotope thermoelectric generators provide limited, declining energy over time. Instruments degrade, materials fatigue, and micrometeoroid impacts can accumulate damage. You notice that planning must account for a comprehensive set of slow but inevitable challenges, each governed by physics and materials science. Propulsion efficiency is another factor. Rockets expel mass to generate thrust. The more mass they carry, the more fuel is required. Carrying enough fuel for interstellar travel becomes impractical for conventional chemical methods. Even high-efficiency ion or plasma drives face the same exponential challenge. Accelerating large masses over interstellar distances demands energy that exceeds current production and storage capabilities. You understand that this is not a matter of imagination but of strict, quantifiable physics. You consider the scale of the universe in perspective. Nearby stars appear close because 4 light-years is minuscule compared to the galaxy's 100,000 light-year diameter. Observing them provides insight, yet physical travel remains constrained by energy, materials, and fundamental laws. You notice that proximity in measurement does not equate to accessibility in practice. The stars serve as observable laboratories, allowing precise study without requiring physical presence. Unmanned probes offer a practical alternative. Instruments designed to operate autonomously can provide decades of observation, collecting data about planetary formation, atmospheres, and stellar activity. Webb itself exemplifies this approach, orbiting far from Earth and capturing infrared spectra without human intervention. You reflect that such missions maximize scientific return while respecting the constraints imposed by interstellar distances. Observation and measurement become the most effective way to study nearby stars. You appreciate that this understanding tempers human expectation. Curiosity remains valuable, yet feasibility must be grounded in physics. Alpha Centauri remains close in relative terms but distant in achievable travel. Scientific investigation relies on telescopes, probes, and modeling to study its stars and planets, rather than attempting physical visitation. You notice that this recognition does not diminish wonder. It clarifies the parameters within which meaningful exploration occurs. Planning for future technology is ongoing. Concepts such as generational ships, fusion propulsion, and advanced light sails continue to be studied, even if they are decades or centuries away from realization. Each proposal is constrained by energy, mass, and distance calculations, all grounded in physical law. You observe that exploration remains possible through imagination applied to physics, not by ignoring fundamental limits. You reflect quietly on the difference between observation and occupation. Understanding Alpha Centauri through instruments, measurements, and simulations allows deep knowledge of its stars, planets, and environment. Attempting to traverse the distance physically introduces constraints that remain insurmountable with current engineering. You notice that insight and measurement are the tools available, offering precise, lasting information without defying physics. You rest with the understanding that distance, energy, and time collectively define what is possible. Even the nearest star requires planning, resources, and patience far beyond human scales. Alpha Centauri can be observed, measured, and understood, but it cannot be reached directly. The practical limit becomes a framework for exploration. Study, model, and infer within the constraints of nature. You begin by allowing your mind to drift back toward Earth, carrying the knowledge of Alpha Centauri's stars, planets, and environments. Observing them from afar reinforces the uniqueness of your own system. The Sun, a single, moderately stable star, provides a consistent flow of energy that drives climate, weather, and the cycles of life. Its luminosity has remained remarkably steady over billions of years, allowing the Earth's atmosphere to develop gradually and maintain conditions favorable for surface water and habitability. You notice that this stability is a quiet prerequisite for the complex processes that have shaped life on your planet. Atmospheric balance emerges as a central theme. Earth's atmosphere contains the right mixture of gases to retain heat, shield against harmful radiation, and support life. Carbon dioxide, nitrogen, and oxygen levels are regulated by both geological and biological processes. Volcanism releases gases from the interior, while oceans, rocks, and organisms absorb and cycle these compounds over time. You reflect on how subtle changes in these mechanisms could shift climate and habitability dramatically. Observing Alpha Centauri's planets highlights how easy it is for atmospheres to erode or become inhospitable when conditions are less favorable. Magnetic shielding contributes silently but decisively to planetary endurance. Earth's magnetic field, generated by the motion of molten iron in its core, deflects charged particles from the sun and cosmic rays from space. Without this protection, the atmosphere could gradually erode under the constant bombardment of energetic particles. You consider planets around Proxima Centauri, subjected to frequent flares. Their magnetic fields, if present, must compensate for high-energy radiation to preserve atmospheres. Earth's field, by contrast, is sufficient to maintain the long-term integrity of the atmosphere and to protect life from harmful radiation. Orbital fortune further emphasizes the planet's stability. Earth follows a nearly circular orbit, which moderates seasonal extremes and limits dramatic temperature fluctuations. The axial tilt, rotating at approximately 23.5 degrees, creates predictable seasons while remaining stable over millions of years. Planetary neighbors, such as Jupiter, exert gravitational influence that stabilizes Earth's orbit. You notice that even minor differences in mass, distance, or orbital configuration could produce climates far less hospitable. Comparing these dynamics with those of Alpha Centauri underscores that habitable conditions are the result of precise alignment across multiple factors. You reflect on the timescale over which these systems operate. Billions of years have allowed Earth to accumulate and maintain water, develop tectonic activity, and sustain a magnetic field. Geological recycling prevents atmospheric stagnation, while internal heat drives volcanism and magnetic field generation. Alpha Centauri's planets, if they exist in the habitable zone, must persist through similar processes. You notice that survival is not guaranteed. Enduring favorable conditions requires the right combination of star, orbit, and planetary properties over immense spans of time. Temperature and radiation offer another perspective. The Earth receives sufficient energy to maintain liquid water without experiencing extreme heating or freezing. Solar output remains within a narrow range, unlike the fluctuating flares of smaller or binary stars. You observe that a planet's position relative to its star, the star's energy output, and the protective factors of atmosphere and magnetic field combine to create a delicate equilibrium. Alpha Centauri's environment, though nearby, demonstrates how small variations in stellar behavior can profoundly affect planetary conditions. Chemical composition also contributes to habitability. Earth contains the elements necessary to sustain life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These compounds participate in cycles that maintain atmospheric and surface stability. Webb's observations of protoplanetary disks confirm that similar materials exist around other stars, but their distribution, quantity, and planetary retention may differ. You notice that the mere presence of elements is insufficient. Their organization within a planet, coupled with long-term stability, determines whether they can support life. You consider the role of time in shaping Earth's resilience. Geological, atmospheric, and magnetic processes act continuously, smoothing short-term perturbations and enabling long-term equilibrium. Plate tectonics recycle carbon and redistribute heat. Volcanic outgassing replenishes gases lost to space. Oceans moderate climate by storing and transporting energy. Magnetic shielding protects against erosion of the atmosphere. Each process operates on a scale that spans millions of years, revealing that endurance is as critical as initial formation. Observing Alpha Centauri reinforces this perspective, illustrating that planets may form in habitable zones yet fail to remain stable over similar spans. Comparing planetary formation also provides insight. Earth formed from a disk of gas and dust around the young sun, following the processes Webb now confirms around other stars. Gravity, collision, and accretion produced a terrestrial planet with appropriate mass and composition. The Moon, likely formed from a giant impact, contributes to orbital stability and tidal effects. You realize that this sequence of events was highly constrained, and minor variations could have prevented Earth from maintaining long-term habitability. Observing nearby systems emphasizes how delicate the balance is, even when initial conditions appear similar. You reflect on human observation itself. Telescopes like Webb provide precise measurements of stellar and planetary properties, allowing you to quantify differences between systems. Spectroscopy reveals atmospheres, disk compositions, and thermal profiles.
Gravitacional modelam clarifies orbital dynamics.
By studying Alpha Centauri, you gain perspective on the forces that have enabled Earth to remain stable. You notice that understanding these processes does not require imagination to fill gaps. Rather, careful measurement and modeling produce reliable, verifiable insight. You appreciate the quiet significance of confirmation. Webb's observations support models of planet formation and stellar behavior. They do not rewrite expectations but refine them, highlighting which conditions are necessary for survival. Observing Alpha Centauri helps you contextualize Earth's habitability. Your planet's atmosphere, magnetic field, orbit, and internal dynamics have persisted in a combination that is measurable, exceptional, and observable. You notice that this reinforces understanding rather than fear, emphasizing evidence over speculation. Finally, you reflect on interconnectedness. Alpha Centauri provides a mirror for Earth, showing both similarities and differences. Its stars are close, sun-like, or smaller, yet the details of their systems remind you that Earth's conditions are the product of precise alignment across stellar, orbital, and planetary factors. Studying these distant neighbors deepens appreciation for your planet's resilience, atmosphere, and ability to sustain life over billions of years. You perceive that scientific observation nurtures calm curiosity rather than urgency, allowing the mind to rest in measured understanding. You rest with the realization that understanding other systems enhances your appreciation of this one. Proximity, mass, radiation, and orbital dynamics all matter, but it is their interaction over immense timescales that shapes planetary survival. Earth's stability is the result of cumulative processes, a combination of fortunate factors observed and confirmed through careful science. By measuring and comparing, you allow insight to arise without exaggeration or fear, and the quiet knowledge of planetary endurance fills your mind.